the Harpies team from Istanbul Bilgi University. This is our first time participating in SUAS and a drone competition in general. Allow us to introduce our group of 4 members. Salih, our esteemed team leader, the expert in avionics and mechanics. Mahmoud, our expert in autonomous control, mechanical design, software, and avionics. Kais, our software maestro, proficient in software engineering, mechanical design, and image processing. Mohammed, our reliable ground station controller, participating in software and a firmware expert. In our hexacopter system, we are using the orange pixel cube for a stable flight control, 6 brushless DC motors with carefully selected probes to ensure efficient propulsion using the motor table, 6 electronic speed controllers, 3 LiPo batteries sustain extended and a calculated flight time. A GoPro camera paired with Jetson Nano captures high-quality footage. A 2D lidar enhances navigation and obstacle detection. In terms of communication and positioning, the HERE Pro RTK GPS system provides precise coordinates. RFD 900 telemetry models enable long-range communication. HERE-Link environments facilitate efficient data transfer. Moving baseline can be used to estimate yaw, in addition to providing position information. This removes the need for a compass, which may suffer from magnetic interface from the ground or the vehicle motors and electronic speed controller. This works even if the GPS don't have an RTK fix, RTCM data from a fixed RTK station or interrupt server. The specification of our hexacopter is 53 minutes of flight time, 40 pounds of payload, and a range of 131,000 feet, which meets the mission requirements. For the camera, we have decided to use the GoPro Hero 12 with the Hyper Smooth feature. It let us avoid using the gimbal mechanism. The cropped image will be passed to the detector, which will return 2 values, color and mask of the object. The mask will be used to select the shape of the object and the algorithm character for the shape detector. We have created our own algorithm. The mask will be passed into your algorithm and our developed algorithm. This algorithm is based on the geometry of the object. First, a contour is drawn around the object. Then, we create lines from the contour. Each shape has a unique number of angles and sides. However, since this is the object, we eliminate the bad lines to get the standard derivation of the length of the lines is calculated, and the only valid lines are used to detect the shape. This method showed 60% increase in accuracy of the detection. We have trained more than 16,000 images of different shapes to train the model on different scenarios. We have built our own image generator where it generates different shapes, letters, colors on different backgrounds and orientations. The YOLO V8 model and our own algorithm will be merged by a simple Kalman filter merging formula. The total confidence score is calculated by multiply confidence gain of the YOLO algorithm by its detection and multiply the shape detector algorithm confidence gain, then summing all up. The character will be created by cropping the inner contour. A YOLO trained model will detect the character. We have traveled more than 17K images on 300 epochs. The cropped letter will be rotated multiple times according to the shape. The cargo drop mechanism have been designed and optimized to ensure safe and fast delivery. The water bottle is descended by a DC motor. We made sure that the torque is enough to lift the airdrop. 5 water bottle is descended with a cap and pin which will drop the bottle into the basket. The servo motor is controlled by ESPN and it will communicate with it on the basket. The servo will control the cap on the basket which will drop the bottle from it. We have split the drop into 3 steps. First step is acceleration, where the airdrop will accelerate. Then it will reach a steady state, where the velocity is constant. And finally, the airdrop will reach the acceleration region to reach full stop at the desired location. The acceleration graph formulas of the 3 cases are identical. It is related to the values of T0, T1, and T desired, where these values are manually chosen. By integrating each formula, we get the velocity formula which we'll use to calculate the required RPM. We have created an Excel file which calculates the KAA and KAD values which will be used to calculate the required RPM. The motor will be controlled by sending a PWM signal. The PWM signal calculated by calculating the error and multiplying it by an error gain which will keep the motor controlled by a feedback loop. When considering between a hexacopter and a quadcopter for a specific formation and tasks, the advantages of the hexacopter stand out. With 6 motors compared to 4, the hexacopter delivers greater thrust, faster performance, and a higher acceleration. Its design allows for more efficient power distribution, resulting in less ampere draw per motor and potentially longer flight time. Additionally, the hexacopter's larger space for payload makes it more suitable for carrying heavier loads. Its 6-axis configuration provides superior stability and control, especially in challenging weather conditions. In contrast, the quadcopter lacks the thrust, stability, and payload capacity of the hexacopter. Thus, for missions requiring reliability, efficiency, and adaptability, the hexacopter proves to be the superior choice. Ensuring safety is essential in all our operations, and we've implemented several measures to mitigate risk throughout our project. During flight tests, we strictly adhere safety protocols, including not taking off until all individuals are at a safe distance from the takeoff point. Our hexacopter is equipped with a safety switch connected to the Pixhawk flight controller, allowing for immediate intervention if necessary. To minimize potential hazards, we conduct all our activities in a stadium, a large and open space with no restricted areas. During our flight test, we employed 2 distant control methods to assess the capabilities of our hexacopter. Initially, we utilized a human interface via an RC controller to gauge the drone responsiveness and attitude adjustments. Observing its reaction provided valuable insight into the flight dynamics. And then we tested the autonomous control using specialized drone kit code communicated via telemetry, getting the longitude and latitude coordinates obtained from Google Earth for optimal accuracy. We executed path following and targeted point navigation tasks. Throughout a combination of physics principle and drone kit functionalities, we commanded the hexacopter to execute various maneuvers, including rotations, speed control movements, and precise positional adjustments across all axes. This comprehensive approach demonstrates our team proficiency in both manual and automated flight operation, showcasing the versatility and adaptability of our drone system.